All right, so we're just going to discuss the Laplace transform. Once we have it down, once we know how to transform something using this special integral, then I'm going to show you how to use it to solve differential equations. So the Laplace transform takes one function and transforms it into another function via an integral. So the Laplace transform is itself a function, and its inputs and outputs are both functions, right? You put in a function, does some fancy stuff via an integral, and then you get a new function out. So this is the definition of the Laplace transform. So it's the integral from, so it's the Laplace, I should write this down. This is the Laplace transform of y of t. So it's the integral from 0 to infinity of y of t, the function you're trying to transform, times e to the negative st dt. So if I want to find the Laplace transform of y of t equals e to the 2t, so that would be the Laplace of e to the 2t. It will be the integral from 0 to infinity. Replace the y of t with the function that I was given, e to the 2t, times e to the negative st dt. Yeah, sorry. Negative st. So I'm multiplying like bases there, so I can add those exponents. So this is the integral from 0 to infinity of e to the 2 minus s t dt. And then how do you take the integral of some stuff?
Integral of the thing times the divided by the integral or derivative.
Yeah, right. All right, so it's kind of like we're doing the chain rule backwards, or we're doing a u substitution. I'm just not writing it all down, right? So the antiderivative of e to the t is e to the t, right? So this is going to be e to the 2 minus s t. But then just think about going backwards. When I take the derivative of this thing, I should get what I started with, right? Because I'm trying to come up with an antiderivative. But the derivative of e to the 2 minus st is e to the 2 minus st times 2 minus s because of the chain rule. So I have to sort of counteract the chain rule by doing 1 over 2 minus s. So that's my antiderivative. And then I evaluate that from 0 to infinity. And now we have to remember how to do the infinite integrals. Yeah, improper integrals. Lost the word for it for a second. All right, so you take the limit as b approaches infinity of 1 over 2 minus s e to the 2 minus s t evaluated from 0 to b. So first, like, how do you plug infinity in? You can't because it's not a number, so I'm going to plug in a b, and then after I'm done plugging it in, I'll take the limit as b goes to infinity. Okay, so first I'm going to plug in a b for t, right? So this is 1 over 2 minus s times e to the 2 minus s b. Just plugging in a b for the t, minus, and now I'm going to plug in a 0. 1 over 2 minus s e to the 2 minus s times 0. All right, so let's think about the limit. Well, what is e to the 0? 1, right? So this term is just 1 over 2 minus s. There's no b's in it at all, right? So it doesn't matter that I'm taking the limit as b goes to infinity. This is just a constant. Always stays what it is. So now I just have to look at this term and think about what happens as that b value gets really big. So e to something, if you're thinking about what happens to that exponent when b gets really big, it kind of depends on 2 minus s, right? Is that exponent getting really big positive or getting really big negative? Depends on what s is, right? So let's say that s is bigger than 2. Then what happens? Yeah, then if s is bigger than 2, then 2 minus s will be negative. And if you let b go really big, this is a really big negative exponent. So e to that thing will be really, really small. It'll approach 0. So this whole term goes to 0 for s is bigger than 2. So this is going to be 0 minus 1 over 2 minus s, which is 1 over s minus 2, if s is bigger than 2. So that's the Laplace transform. I took a function of t, y of t, and I transformed it into a new function of s. Nope.
Now, would that be negative one?
No, so I used this negative to change the order of the subtraction. So this is our notation for the Laplace transform. It's just like cursive L of y of t. So it takes a function in terms of t. You apply the Laplace transform and you get a new function in terms of s. Right. Yeah, we don't care. Yeah, we need it to converge to something. Yeah.
It was just trying to find the values of s, which make the e term go to 0.
Yeah.
Which make the first term go to 0.
Right. Yeah. So the Laplace transform of e to the 2t is 1 over s minus 2. Notice the 2 shows up in both places. That's not a coincidence, right? So just as a conjecture, right, what do you think the Laplace transform of e to the 3t is? Yes. For s greater than 3, yeah. And then the Laplace transform of e to the at, 1 over s minus a, s greater than a, yep. So these are just conjectures at this point. Let's verify that that is actually the general form for e to the at. Okay. So I want to compute the Laplace transform of e to the at. So we're just going to practice doing this via the integral one more time. So this is the integral from 0 to infinity of y of t, the function I'm trying to transform, times e to the negative st dt. It's going to be almost the exact same process as before. It's just instead of having a 2, I have an a. So these are multiplying like bases. I'm going to add the exponents. So this is e to the a minus st dt. And then take the antiderivative of e to the a minus st. So this is e to the a minus st, and then times 1 over a minus s to sort of counteract the chain rule. And I have to evaluate that from 0 to infinity. And this is a similar thing is going to happen here. I'm going to take the limit as b goes to infinity of 1 over a minus s e to the a minus s t from 0 to b. So if I plug a b in, I have 1 over a minus s e to the a minus s times b. And then when I plug in a 0, I get 1 over a minus s, because e to the 0 is just 1. And then this first term, that goes to 0 if that exponent is negative, which means that s would have to be bigger than a. So when I take the limit, I get 1 over s minus a if s is bigger than a. So this is the first entry in your table of Laplace transforms. So you can always start with the definition and come up with the Laplace transform. But when you start using these a lot, there are really common ones that you'll see, and you can look them up in a table. So this is the first one that's in your table, and we'll know like 5 of them by the time we're done with chapter 6. Okay, so some properties of the Laplace transform. This is what makes them helpful for solving differential equations. It has this really nice property that says the Laplace transform of a derivative is s times the Laplace of y, like the antiderivative of the thing you started with, minus y of 0. So it's a way of sort of like getting derivatives out of your equation. So I want to verify this one before we go on to the other properties. It's a really important one. So I want to take the Laplace transform of y prime. Right here I wrote it as dy dt. Now I'm writing it as y prime, same thing. So I'm going to use the definition, right? This is the integral from 0 to infinity of dy dt times e to the negative s t dt. Yeah, I don't know why I wrote it. I think I just wrote it as y prime the first time because I was being lazy. Yeah, so the dt's cancel out. Yeah. I'm just going to leave it for now, but so this is a product, right? dy dt times e to the negative st dt. So typically, when you see a product in an integral, you think either u substitution or what's the other one? By parts. Yeah. So we're going to do by parts. All right. So in by parts, you have to choose a u and a dv. And you typically choose, well, you typically choose dv to be the most complicated looking thing that you can still integrate. But I'm just going to tell you how to do this. All right, so e to the negative st, that's going to be my u. And then the dy dt dt thing is going to be my dv. Okay, so u is e to the negative st, and dv is dy dt times dt. So really, now I'm going to cancel the dt's, and I say, okay, well, dv equals dy, which means v equals y. So I've got the dv. I chose a dv, and I calculated v. I chose a u. I need to calculate a du, which is negative s e to the negative st dt. And then I go back and I apply the by parts formula. It says the integral, it should be u times v minus the integral of v du. Same bounds, 0 to infinity, 0 to infinity. Okay, so u times v, that's y, yeah, that's okay.
0 to infinity minus integral.
Yeah, it's just the formula for integration by parts. Yeah. So this is a lot of work proving this property. Once it's proven, you're just going to use it a lot, right? So like it's good for you to like follow along and see where this comes from. I'm not going to like test you on proving this, just so you know. Yeah. For du, I just multiplied both sides by dt. I was calculating du dt. And I did an extra step. I said, well, du dt would be negative s e to the negative st, and then I multiplied both sides by dt. All right, so u times v. So v is actually y, and u is e to the negative st. So I have y e to the negative st. That's u times v minus the integral. And this is from 0 to infinity. Okay, a v du. All right, so v is y. Du is negative s e to the negative st. dt.
So like in the integral there was 0.1 and like
Okay, so I chose so for my by parts, I chose u. U is just plain old e to the negative st. There's no dt in it, right? There's no dt in the u, right? So there's my u. My dv was dy over dt times dt. You're good?
Yeah.
All right. Okay. Again, I'm proving something, like, so it's good for you to see where it comes from, but the how to do by parts, yeah.
We use computers to do that in our later engineering classes.
It was from this. It was from this negative. Yeah. Yeah.
How do you algebra again? It's been a while.
Okay. Let's think about this first part, where I have to do y e to the negative st from 0 to infinity. So t is the thing that you're plugging in, right? So as t gets really, really big, that's e to something really, really, really negative. So that's going to go to 0, right? And then when I plug 0 in, I just get y. All right, so this is going to be y. Hold on. No, when you go to infinity, you get 0. No, the whole, it's, yeah, it's e to the negative infinity, which is 0. It's not e to the 0. So this, when you put infinity in for t, this whole term goes to 0. When you put 0 in for t, you get e to the 0, so this is just y.
So we get negative y.
So it becomes negative y. Yeah, negative y. Yeah. Yeah, so it's 0 minus y. And remember y is a function of t, right? So if I'm plugging 0 in, this is actually y of 0. Now to deal with the integral. S is a constant, so I'm going to pull it out of the integral. And I'm going to pull this negative out. So I'm going to have plus S times the integral from 0 to infinity of y e to the negative st dt. All right, so you might think like, oh my God, do I have to do by parts again on that thing, right? You don't, because this should look familiar. Y is really, like I said, a function of t. And this is the definition of the Laplace transform. So this is equal to negative y of 0 plus s times the Laplace of y of t. And that's the property that I was trying to prove. Because y is really a function of t, right? So when I'm plugging in infinity in for t, that term goes to 0, but now I'm going to plug zeros in for the t's, so I have y of 0 times 1.
So that was a Laplace transform.
Yeah, that's the definition of the Laplace transform. So that's the most important property of the Laplace transform. It's the hardest to prove. These other two we're going to use a lot, and they just come from straightforward properties of integrals, right? The integral of a sum is the integral of f plus the integral of g, right? And if you take the integral of a constant times f, you can pull the constant out of the integral. So these two follow directly from properties of integrals, and we won't take the time to write it all out. So we've got three properties that are going to really help us solve differential equations. All right, so now I'm going to show you how it works. We've got this Laplace transform. It transforms a function of t into a function of s. And we have some properties of the Laplace transform. So the idea is I have an equation. One of the first things you learn when you're solving any equation is that you can do whatever you want as long as you do the same thing to both sides, right? I'm going to take the Laplace transform of both sides of this equation. The Laplace transform of y prime equals the Laplace transform of y minus 4e to the negative t. And I'm saving this little piece of information for later, the initial condition, which you have to have in order to use Laplace transforms to solve the differential equation. You can't find a general solution. You can only find the solution to an initial value problem, which is a particular solution. All right, so we just spent some time proving a property about the Laplace transform of a derivative, and it was negative y of 0 plus s times the Laplace of y. So that's just the Laplace transform of y prime. And then on the right, I'm going to use some of my other properties that lets me break this up into the Laplace of y minus 4 times the Laplace of e to the negative t. So I used the property to let me break that up into two separate Laplaces, and then I pulled the negative 4 out of the second one. All right, I'm going to gather all my terms that have a Laplace of y in them onto the left side. So this term and this term I'm going to put on the left and move everything else to the right. So I have S times the Laplace of y minus the Laplace of y equals y of 0 minus 4 times the Laplace of e to the negative t. But what is y of 0? 1. I happen to know that because it was given as my initial condition. So I'm going to erase that and put a 1. All right, on the left side, both of these terms that I collected over here have a Laplace of y in it. I'm going to factor out the Laplace of y. I have s minus 1. All right, the Laplace of e to the negative t, I know. I can actually do that. That's e to the at, which was 1 over s minus a. Yeah, so this is going to be 1 minus 4 times 1 over s minus a. Yeah, in this case, a is a negative 1. E to the negative t. It doesn't say e to the at, it says e to the negative 1t. So I use negative 1 for a. All right, I'm going to solve for the Laplace of y. The idea is I want to find out what y is, right? That's the solution to my differential equation, right? I'm trying to find a function of y so that y prime is y minus 4 e to the negative t. All right, so I'm going to solve for the Laplace of y, which is like close, almost y. So if I have the Laplace of y, yeah, you can do this without Laplace. So this is 1 minus 4 over s plus 1. So I now know the Laplace of y, which is really close to knowing y, right? The Laplace of y and y are just related by an integral. So I need to like be able to go backwards. Right? If I give you a y, you can calculate the Laplace of y using the integral I gave you, or maybe a table of Laplace transforms. So I just need to go backwards and I'll be done. Oh, I'm sorry, I didn't write it down. I just copied the right-hand side. 1 over s minus 1 minus 4 over s plus 1, s minus 1. All right, so I know the Laplace of y. I'm close. I just need some way to go backwards. So I'm just going to use the inverse Laplace. So y is the inverse Laplace of 1 over s minus 1 minus 4 over s plus 1, s minus 1. I only have one Laplace transform that I know. I know that the Laplace transform of e to the at is 1 over s minus a. So I'm just going to write this rule down. The only thing we know right now is that the Laplace transform of e to the at is 1 over s minus a. So if I ask for the Laplace of e to the 2t, you know it's 1 over s minus 2, right? But if I give you 1 over s plus 1, right, what is the Laplace, what is the inverse Laplace of that? e to the negative t, yeah. So the Laplace of e to the negative t, right? So you can go in both directions with this rule. What about 1 over s minus 1? That's e to the t. That's right. So I need to take the inverse Laplace of 1 over s minus 1. That's e to the t. So this part, 1 over s minus 1. If I need to go backwards, take the inverse Laplace, you get e to the t. The Laplace of e to the t is 1 over s minus 1. This part's a little harder, right? Because I have two things in the denominator, s plus 1, s minus 1. Do we have like some method that you learned maybe in Calc 2 for breaking a fraction into a sum of two fractions with simpler denominators? Partial fractions, yeah. Let's do that on another page. So before I do that, I'm just going to write down where we're at. This is minus the inverse Laplace of 4 over s plus 1, s minus 1. So I'm not lost when we come back after we break that apart. So I took the inverse Laplace of 1 over s minus 1, got it. Now I'm going to do the inverse Laplace of 4 over s plus 1, s minus 1. So I'm going to break that up into two fractions so that I can use the only rule that we know. All right, so I'm going to break this up using partial fractions, a over s plus 1 plus b over s minus 1. Multiply both sides by your common denominator, s plus 1, s minus 1. And over here, everything cancels and you just get a 4. And over here, the a fraction, the s plus 1s cancel. So I have a times s minus 1 plus b times s plus 1. All right, so if you learned this from me, I did it by equating coefficients, but Ian showed me a niftier way to do this. This equation has to be true for every s. So choose a convenient s, right? So like if I chose s equals 1, then this equation would say 4 equals a times 0 plus 2 times b. And then this term goes away, right? So that was a convenient choice of s because now I only have one variable and I get b is 2. What would another convenient choice of s be? Minus 1. So this says 4 equals a times negative 2 plus b times 0. So that term goes away, solve for a, and you get negative 2. The other method was to distribute. So you have 4 equals as minus a plus bs plus b, and then gather your s terms. So you have a plus b times s, and then gather your constant terms, negative a plus b, and you say, okay, there's no s term on the left, so a plus b equals 0, and the constant term on the right equals the constant term on the left, and you have two equations with two unknowns. All right, so a was over s plus 1, b over s minus 1. All right, going back to where we left off. Y of t equals e to the t minus the inverse Laplace transform of, I'm just replacing 4 over s plus 1, s minus 1 with two separate fractions that we just calculated. So I have -2 over s plus 1 plus 2 over s minus 1. Now use my nice properties of Laplace and inverse Laplace that says that I can do the inverse Laplace of each of those, and I can pull the constants out front. So I have y equals e to the t minus a negative, so I made that a plus. I'm going to pull the 2 right out, times the inverse Laplace of 1 over s plus 1. And then I have minus 2 times the inverse Laplace of 1 over s minus 1. So what's the inverse Laplace of 1 over s plus 1? E to the negative t. And then I have minus 2 inverse Laplace of 1 over s minus 1, e to the t. Combine like terms here. So I have y equals e to the t minus 2e to the t. So I have 2e to the negative t minus e to the t.
So right now, are you essentially saying that we've got a K1 of 2?
Yes. So it must have been that the eigenvalues were -1 and 1, right? So the general solution is k1 e to the negative t plus k2 e to the t, and then using my initial condition, I got 2 and -1.
Somewhere down the road.
Well, this particular differential equation had forcing, right? So this would have been a 3-step process, right? Solve the homogeneous system, like then guess a particular solution, add them together, then solve for your constants. It would have been a long process. The trick is, like, the key point is this, right? That we have a formula for the Laplace transform of a derivative. And that takes all of the derivatives out of your equation. So now you can just solve it using algebra. Everything we did here was algebra. Moving stuff around. I took the Laplace transform of some stuff, but I didn't even use the integral. I just used like a formula. And then I did partial fractions, but that's just an algebra technique. I didn't use partial fractions in order to calculate an integral. I just separated a fraction. All right, so I think probably you need some practice.